Hello everyone, today I want to talk about some lubrication. So the lubrication is one of the important issues in practical engineering. We know that under the low linear velocity on the rotor surface, sliding bearing is generally used. In order to prevent the joint friction, the gap between rotor and the bearing is full of the lubricating oil. However, as being rotating in the bearings, the rotor is not in the concentrate position, so which could be seen in this figure. The gap delta between the rotor and the bearing is varied along the rotating directions. The ratio of the gap of the delta, and the radius of bearing R is much smaller, so the surface of both rotor and the bearings can be treated as planes. And the flow of the lubricating oil between the rotor and the bearings can be nearly treated as the flow of inclined planes, so which can be seen in this figure. Alright, so first we make the assumptions. So first we will see the assumptions. The first one is the upper plane is moving in a straight line with a velocity of the u. So this can be seen here. So the second, that the gap is full of the lubrication oil. And the third would be the length of the rotor and the bearing is long enough, so the flow is treated as plane flow. So this would be the plane flow. Okay, so the gap delta and the deep angle alpha are both much smaller, so the velocities in y directions is much smaller than that in the x directions, and the variation in y directions is much smaller than that in the x directions, right? So the comparisons can be described as below. So the comparison, so let's see from here. Alright, so this is our expression 1. And also the inertial force per volume is, the inertial values would be and the viscous force per volume is the Reynolds numbers is the Reynolds numbers will be F inertial, F viscous, and we use this, divided this, and finally we might got that one. We got that one, right? Alright, so this is our equation 2. So if this one is much smaller than 1, so then the inertial force can be ignored compared to the viscous force. So the governance equations can be expressed as, the continuity equation is, alright, so the continuity equations will be, so this is our equation 3. So the AS equations are so this would be our equation 4 and 5. So this is the NS equations. So where this one So and that ones can be defined as effects of pressure and viscous force on the creeping flow respectively, right? All right, so we know that because of this, so because of this, so this can be proved, right? So compare the governing equation in x and y directions. Now we can get that one, right? So if we assume that we assumed we're equal to 0. So the pressure is the function of x. So the following equations can be simplified as, so now we simplify the equations and we can get that this is the first one and second one might be zero, and the last one might be right. Okay, all right. So finally we can get that one, and then the boundary condition of the creeping flows are, so here our boundary condition for this could be alright, so when y equals delta, u would be equals to 0 and we would be 0. So, and finally, so through the integration and the deductions, and finally we can get the velocity u in the x direction. So the final one would be u will be equals to alright, so this is our final result. So thank you.